Okay, here we have another example of support reactions in 3D. Let's read the problem. It says, determine the support reactions at the smooth color. Every time that you read and try to fish for clues, smooth colors, a smooth color A, and the normal reaction at the roller support B. So this is a roller, this is a smooth color. Once again, a smooth color means these can slide and these can rotate around that. Because if I have this welded, it's different. But this is not welded. This can rotate perfectly in that direction. It can slide in this direction. So basically, because of that, the reaction that I have is one reaction there, which is called AZ. I don't have any reaction in the X direction, and I have another reaction also in the Y direction. Because it's obvious here, you see. This is here, and this is stopping it from going there. So this is going to be AY. What about moments? Well, moments, I'm going to put the moments in this color so it look different. As I said, about X, because this is smooth, it's not producing any moment. About Z, yes, it is producing a moment about Z, because this is not going to rotate in this direction. And I'm going to put the double arrow here also to represent the moment. I'm going to call that moment A. Z. And what about Y? Can this rotate like that? No, it can't, because basically what the structure is this, and this portion is preventing this from doing that. So I'm going to have also a moment going in this direction, going outside. I don't know if it goes outside, but I'm going to put it outside, and you remember the sign is going to tell me in what direction goes. So this is going to go in this direction, like that. It's coming out, and this is called MAY. What else do we know? So that's our given. We have the forces. We already know that it's a smooth color, and also that is a roller. So given. We're asked to calculate reactions, and be very careful when they ask you for reactions, because that means forces as well as moments. So reactions at A and B. That's what we have to calculate. Reactions at A and B. How are we going to do this? Well, this problem I want to solve it in two different ways. The first way, I'm going to use the Cartesian approach. And second, I'm going to use scalar equations. You don't have to do both. I'm just going to do both of them for demonstration purposes. So for the first part, let's start with the Cartesian approach. Let's do it. Any other reaction that I'm missing here? Yes, of course, I'm missing this reaction. It's a reaction at B, and this is going to be called By. Using the Cartesian approach implies that we have to express everything as a vector. So summation of forces, but forces as a vector has to be 0. Okay, what forces do I have? I have the reaction force at A. That reaction force at A is going to be AYJ plus AZK minus 800J, K minus 600K plus BZK. I put here BY and I meant BZ. BZK equal 0. Now basically we can just match everything that is I with I, everything that is J with J, and everything that is K with K. So what do we have in Y? In Y we have that AY in J and nothing else. So AY is 0. What about K? Well, in K I have AZ minus 800 minus 600 plus BZ equals 0. Or I can say that AZ plus BZ equal 1400. And I'm going to call that my equation number 1. Now, let's do summation of moments about A, once again as a vector, has to be 0. And let's start with a support. At this support I have MAZ K. I'm going to have MAY J. Those are the moment reactions for A. Now, I have this force, and this reaction here. That means that if I'm going to use the vector approach, the Cartesian approach, from this point I have to express my R and another R from here and the other R to there. So basically I'm going to have this R, I'm going to call this R1, R2, and R3. R1 multiplied by this force. What is this R1? This R1 is 0.8. 0.8 what? 0.8 J cross multiply by this force, but this force is negative 800 in the direction of K. That's that value. Now the second R2 cross this force, the R2 is going to be from here to here and from here to here. So this distance from here to here is 1.6 J. That's my R. And from here to here is going to be negative because I'm going to the negative direction of X, negative 0.4 I cross multiply by this force, and that force is negative 600 K. And finally the last R, this R here is gonna be 0.8 plus 0.8 is 1.6. 1.6 in the direction J, and in the direction negative X, because I have to go back. This is X positive, I'm going back, so this is going to be negative 0.8 I cross multiply by this force, but this force is BZ in the direction K, and that has to be equal to 0. This method doesn't take too much of a thinking, but you have to work. You have to work for it and be really careful with the details. Now let's do the multiplications. Let's use our circle I, J, K, and then I'm going to say that everything that I cross multiply in this direction is positive, otherwise it's negative. So let's keep going here. I have MAZK plus MAYJ, and then I have J cross K. Well, J cross K, if I go in this direction, is positive, but it happens that I have this negative sign, so yes, J cross K is positive I, but because of this negative sign, it's going to be negative 640 I. Now I have J cross K, same thing, and I have the negative sign there. That means that I'm going to have negative 960 I, and now I have I cross k. I cross k is negative j, times negative is also negative. It's going to be negative 240 j. Now keep going here. J cross k is positive I. So it's going to be plus 1.6 bzi, and I cross k is negative j, but I have a negative sign here, so it's going to be plus 0.8 bzj equals 0. And once you have your equation like that, the only thing that you have to do is decompose that in equations. You have to put that into equations, basically. This is a I cross k. Yes, this is I cross k. Okay. Now let's start grouping everything together. Let's first go with the summation in I. What do I have in I? In I have MAAY. What else? No, this is J. Let's do it in J first. MAY, and this is negative 240 plus 0.8 bz. There's the summation of everything that goes in I now. I have negative 640, negative 960, plus 1.6 bz, which basically tells me directly that bz is equal to 1600 divided by 1.6 is 1000 Newton. Now I can get this bz and plug it into this equation that I got here, and then I can get that MAY minus 240 plus 0.8 times 1000 equals 0. So MAY equal negative 560 Newton meter. And what else? Let me put another piece of paper here because it's almost no more paper. Now I do everything that goes in K, and everything that goes in K is MAZ, and there's nothing else, so this is going to be equal to 0. The only thing that we can add to this problem to make it more, I'm not going to say exact because the problem is correct, is expressing this direction. So what I have to say is, if this is my y, this is my z, and this is my x-axis, that moment in y, originally I was assuming it going into that direction, but the moment in reality goes into this direction, negative direction of the, like that, entering into the negative side of the axis. And this is 560 Newton meter. That would be the only thing that you can add to that problem. So go again, review this problem again, go through it and try to understand what I did. This is the first procedure. Now let me explain you the second procedure for this problem. The second procedure would be using just scalar equations. Scalar equation of equilibrium. So let's use procedure 2. Scalar equation of equilibrium. Of course, we need to put our reactions that we had before. We studied them before. I'm not going to go through those details again on how do we analyze that. This is AY, this is AZ, and also I have a moment. I don't have AX, but I have a moment coming here in this direction. Which is called MAY, and I have another moment going in this direction, which we call MAZ. And I'm assuming the moment positive. I know it's going to be negative because we already calculated, but anyway, I'm going to assume it positive. And remember, we also have this reaction here, BZ, and that's basically what we have. Now, what is the procedure for doing a scalar equation of equilibrium? Exactly the same thing. Let's do summation of forces in X equals 0. So if we do summation of forces in X equals 0, let's see what is happening in X. Do I have anything in X? I don't have force. I don't have anything. Nothing. There's nothing acting there. So let's do now summation of forces in Y equals 0. Y is this direction. So then I have AY, equals 0. Nothing else. And then summation of forces in Z has to be equal 0. So I have AZ there, and BZ minus 800 minus 600 equals 0, or I can say that AZ plus BZ minus 1400 equals 0, which looks pretty much like the equation that we got before here. This is going to be my equation number 1. And what else? I have everything there. So now let's do summation of moments, because I already did summation of forces in X, Y, and Z. So let's do summation of moments with respect to Z equals 0. And Z is this axis. What do I have here? I have a moment called MAZ, which I assume positive in this direction. And let's see, do you see any force here that can make this element rotate about the Z axis, the vertical axis, like that? Because this force is not, and this force is not. The only possibility, if it was a force in this direction, that will make the object rotate about the x-axis. But these forces are parallel, the three of them, with respect to the z-axis. And remember, forces parallel to the axis is not going to produce a moment, because force and distance has to be perpendicular. So moment with respect to z is 0. Now summation of moments at A with respect to y, that has to be 0 also. Let's see that. Y is this one. So I have MAY. Now this force is producing a rotation, yes, but the rotation this force is producing it is with respect to x-axis, not y. This one here. This one, if I apply the force here, that force here is causing a rotation of the axis. I don't know if you see it in this direction, like that, like corkscrew in. So basically it's gonna go in like that if I push this point here. That means that it's gonna be negative first at all, because it's going in, and it's gonna be 600 multiplied by this distance, and that distance is 0.4. And this BZ here is the opposite. This point is going to lift and it's going to come to this side. If I apply that, it's going to be something like that. So basically it's a positive force, which is going to be Bz multiplied by 0.8. And from here, I still can't do anything because I don't have Bz anywhere. So if I do summation of moments with respect to x, from here I can just express one equation and say may minus 240 plus Bz times 0.8 equals 0. And if I start with summation of moments at a with respect to x equals 0, and that's the original one, that's the one that I was supposed to start with. I'm just showing you what happened when you start from the point that you shouldn't start with. So if I start with summation of forces in moments in x, I don't have any moment here. This force is producing a moment about x, and it's gonna go negative because just see it. If I apply this, the rotation is gonna go inwards. So negative 800 multiplied times the distance, which is 0.8. Now this one here is also producing a rotation about this point, but the force is here, and the one that is going to produce a rotation is that distance about x-axis, and it's going to be negative 600 multiplied by this distance, which is 1.6. And this force also, same distance, is going to produce a rotation, now rotation in this direction. So it's going to be plus 1.6 Bz equals 0. From here, I can solve for Bz, and Bz is going to be equal to 1000 Newton. And I can put this Bz into this equation, and then I can get my May equal negative 560 Newton meter. And if I want Az, I can put this into there, and then I can get that Az is going to be equal to 400. Correct? Yes, 400. Because it's going to be 1000 minus 1400, it's going to be negative 1400. When I pass it to the other side, it's going to be 400 Newton, which, by the way, are the values that we got before. 400, 400, negative 560, negative 560, Bz is 1000, Bz is 1000, and the moment is 0. So this is the other way. This is a lot faster to do, but of course you have to start imagining what is engineering, by the way, because that, I'm not saying this is not engineering, but this is mostly math. You set up your equation, you set up your math correctly, and you don't care about anything. This one is a little bit more of interpreting and analyzing, but look at just by looking at the drawing, don't look at the numbers, look at the numbers over there and look at the numbers here. It looks like this has a lot of more work to do. And that's true, because some of the considerations that cross product does over there, I'm doing it by thinking the direction of the rotation. So this is the second problem that I wanted to bring for you regarding 3D support reactions. Have a nice day.